and today he's going to talk more about neutrino mass models and model building, his expertise. And yeah, so feel free to start now.
Okay, good afternoon, everyone. So after first lecture, today first let's summarize what so far we have learned. Okay, so I'll do both. Today I think mostly I'll do Blackboard, but also like I'll show the slides also. So far what we learned, like the solar neutrino problem. Atmospheric neutrino anomaly, which appeared also in the mid-90s. So basically, from the solar neutrino, the experiment which where we are seeing the deficit of the neutrino, these are like I'm just writing down all the experiments in those page. The experiment. Stage. Okay. So far we have discussed about these three type of experiment. Okay. First, the experiment which done by Redev is this chlorine experiment. As I said, like you basically solar neutrinos are coming, and then you basically filter out the argon, and from there you look for the solar neutrino. So there we find deficit, like deficit of the solar neutrino, as I said, mentioned like 2/3 was missing. So that's what we get in the chlorine experiment, starting in the early 60s. A similar type of experiment, these are called radiochemical experiment. Yeah, before going to neutrino mass model building, I'll just give you the overview why we go to neutrino mass model building or why we require neutrino mass and mixing. So just I'm summarizing here. So these are the two sets of experiment. Like with chlorine, you give, then you produce this argon and electron, and that's where the deficit comes from. Then in early 80s Kamiokande experiment, as I said, this is something different from these two experiments philosophy. Here, you look for from the these are called water Cherenkov experiment. So these first two sets of experiments almost same philosophy. Okay, so just with referent material with gallium, these are called gallium experiment. Like same solar neutrinos are coming in, and then it goes to germanium, and then you filter out germanium, and that's how you look for the solar neutrino. All these experiments are looking some like finding same thing, same features, like deficit in the electron neutrino promise. Then there is defined experiment coming, and you may ask why you have like different type of search strategy here, because this experiment was not built to look for solar neutrino. This was built for nuclear decay experiment. You have a huge water tank, water Cherenkov experiment where you look for this scattering, and looking at this electron scattering, you basically look for this solar neutrino. And looking at the electrons, you can talk about the, like you can infer the directionality also. So that experiment also see the deficit of the solar neutrino. So these are the summary of the solar neutrino experiment, and all are more or less consistent, and all these experiments finding some deficit in the solar neutrino. Then when these solar neutrino things settled in the first place, like the solar neutrino problem, or what further informations we conclude from defined experiments. So the crucial experiment was snow experiment. I'll talk about it later. So this is called Sudbury Neutrino Observatory. It's in Sudbury, Canada. This experiment plays a crucial role. It's a Nobel Prize winning experiment because I'll tell you just now, there you have a three system equations. I'll write down all species. And the result was published in 2002. So there is something special in this experiment compared to this. Here you just find the deficit. But I yesterday showed some plot where if you add up to all these nu E, nu mu, nu tau flux from sun, you have expectation you will get nu E. But this is the first experiment which was looking for nu mu and nu tau from the sun. And that you can get only when like this one flavor oscillates to another. So they have heavy water instead of like this type of chlorine experiment and so on. Like here it has heavy water. Mr. McDonald got Nobel Prize for this experiment. So if you see, this is a neutral current interaction. If you have heavy water, you have all flavor neutrinos you are producing. And then if you look at this process, it's like 100% like charge current interaction, so nu E. So basically you have three system equation, you can disentangle, and then you can infer like nu E, nu mu, and nu tau flux from this three system equation. Let me share the slide so that so look at these slides. So you have these three type of equation, and you can see the first equation which I write it down, that is this one where you have like three neutrino flavor. You have this one nu E only, and this is you have some certain portion of nu mu and nu tau. Because this equation, if you look at, like there are charge current as well as neutral current. So that's why for the nu E, it's like compared to like 0.15 comes from the neutral current interaction. So then you can add up this, you see this here in the left panel, like you see that mu and tau flux, nu mu and nu tau flux from the solar neutrino we are looking at, and nu E flux. As you can see, it's non-zero. For the three equations, I'm writing down three things. This is a famous plot. And as you see that like this leads to the conclusion that if I collect all the nu mu flux and nu tau flux also from solar neutrino, this adds up to 1. So that means although you are producing in the sun like this nu E, it's through the path, it oscillates to defined flavor nu mu and nu tau, and it adapts to 1. So that was very interesting to conclude this. Somebody has some question?
That's my message. That's my message.
Okay, that's great. Yeah, so that's the thing. So that's how the snow experiment at least settle that you can like few years, like it was very consistent with oscillation phenomena. You can explain this deficit as well as like total flux adding up to 1 that you can conclude. But that's not the end. And also in between, as I said, atmospheric neutrino anomaly, they are also Okay, also atmospheric neutrino anomaly already I yesterday discussed, but just summarizing the thing that you can write down also for the atmospheric neutrino the oscillation probability like 1 minus sine square 2 theta sine square delta m square L over 4E. Let's talk about one particular panel. So these are the outgoing events which I showed, like which is traveling say 30 kilometer in the earth. And from the down, suppose say it's traveling almost like 10,000 kilometer. The one which is traveling like 30 kilometer, like it's almost like the oscillation probability of 1. Like if you look at this oscillation probability, muon survival probability, it's like L, you know, roughly length. Energy also, you know that the neutrino energy, what it can be. So only unknown quantity was delta m square. Now, if you look at the data points are these ones, and the expected one, if you see the continuous the distribution. So the deficit was in the left bottom things, like you are almost getting half of the muon neutrino which you are expecting. So how you can infer delta m square from here? So if you see like from the 0 to 1 zenith angle, like which are traveling very small distance, they're almost probability 1, and this is the equation. So if it is length is very small, so then you can see that it's almost like 1. But whenever you are coming to like it's traveling long distance, 12,000 kilometers, L is very long enough. So then it's like fluctuates super fast, and you can write down in terms of like P mu will be like a survival probability of mu to mu will be. So 1 minus half sine square 2 theta, yes. So and now if you see almost here, like it's half of the expectation. So to get from this oscillation probability to half, you see that sine square 2 theta needs to be 1. Okay. So now you back calculate and match like which delta m square you require. That's how you get to the conclusion of this delta m square and this particular angle. That's how then different experiments comes, and then that also confirms these things. Several experiments comes. So that's how atmospheric neutrino anomaly almost like solved. But for the solar neutrino, still there are some problems. How it was resolved, I already mentioned. So you basically write down neutrino propagation equation in weak basis. If you clearly see that, like it's not like the off-diagonal terms are non-zero. The reason is that, as I said, you produce neutrino in weak eigenstate, but when it propagates, it's a mass eigenstate. So if you are writing down this propagation equation in, say, for the two neutrino hypothesis, you are writing it down, then you see that there will be off-diagonal term because it's an admixture. Like you can write down nu E in terms of 3 mass eigenstates, but here I'm just writing for two neutrino system. Like, so that's why there are off-diagonal terms. Now the thing is that if you have matter effect in addition to that, so then the picture changes, because let me write it down somewhere here. Yeah, basically the characteristics energy you write down E square is P square plus M square. So now if you have for the neutrinos, this A is coming from this matter potential which you developed. Like last day I was showing the diagram. So due to this, if you develop some matter potential, and because it's you are writing in nu E and nu mu, so there is no other term. Because in flavor diagonal basis, it's only nu E can appear this type of charge current interaction. So you have only a term there. So now the thing is that if you clearly see the equation, and this A will be like square root 2 GF NE. number density. This is a quite complicated system of equation because this A is not constant. Whenever you are in sun, inside the core, your A is too dense, and then whenever you are going out, like this A is varying. Basically, this A is function of time. So basically, it's a quite complicated equation. But let's try to understand like this diagram because this is very important. So that's why I'm showing again. So when you are in solar core, where matter density is quite high, so then you can see that if this is too high, that one is too. Yeah. So there are two quantities. So let's write down delta m square 2e, this part, delta m square mass splitting over 2e is very, very less than A. So whenever you are in solar core, so A is too dominated. So whenever A is too dominated, then you can see almost like it's the flavor state almost in the mass eigenstate. Okay. So that means the survival probability will be. So there are two scenarios. Scenario A, whenever delta m square over 2e is very, very less than A, you can see the probability will be only sine square theta. Okay. So, and that's what we are getting in chlorine experiment 1/3. Okay. Now, go to a region like where the neutrinos are like produced like from the solar core. If you are going out here, matter density is small. So then consider this extreme scenario where delta m square over 2e, energy is too small, then this will dominate. And that will be completely vacuum oscillation. Their MSW effect will be not there. Now here you compute the PE. So that will be again 1 minus half sine square 2 theta. Now plug this number. From here, you know that it's 1/3, which is roughly 0.3. Plug this number here, you will get roughly 0.6. You see that depending on the energy of the neutrino in two different regions, if I detect two different energy neutrino, I am getting two different survival probability of electron neutrino. So how does it look like? Yeah, sure. Okay, so this is scenario A, and this is scenario B. So if I writing down electron neutrino survival probability as a function of energy of the neutrino, you can clearly see from scenario A where energy is like when these things like energy is like the matter potential is too dominated over this delta m square over 2 eta, we are getting 0.3. Okay. Now, whenever you are going to low energy of the neutrino and it's getting dominated over this, and they are almost like matter effect and the what. So there you are getting oscillation probability 0.7. So not only the deficit, in the experiment, we are also seeing such data like 0.7 or 0.6, so better to say. So depending on, so you are getting some energy dependent, some observable. Electron survival probability in say in higher energy of the neutrino, which I showed yesterday in boron neutrino and so on, they are getting 0.3, and for the PP neutrinos, those are low energy neutrinos, then you are getting 0.6. How you will explain that? With just the oscillation. It's hard. So you need to then, and that's this famous MSW effect. which explains this transition. Okay, so basically here you're almost like vacuum oscillation, and here you have matter effect, and in between then you need to properly take into account this propagation equation. And as I showed, and that's kind of consistent with the solar neutrino data. And that's what I'm showing it here. So as you can see, the thing I draw, like these are the data. Like these are like almost 0.6, and these are the in the high energy, like it's 0.3. And this was explained, this can be very well explained by this MSW effect. So, and later, like after Borexino in 2011 papers, if you see, there are more data comes from the say PP neutrinos and so on, which are consistent, but still, like there are between 3 to 5 MeV. So there are not enough not enough data to say something about it. So like so far, that's the scenario for solar neutrino problem. And more or less, this MSW like this hypothesis perfectly fits this kind of scenario. And the first experiment, like which exclude the hypothesis of neutrino magnetic moment and basically neutrino magnetic moment. That was this Kamland experiment. Kamland experiment is the first experiment. So far, we have seen only deficit. It's not like we never see the oscillating behavior. Okay. In the Kamland experiment, first they see the survival probability as a function of L over E, some oscillating features. So that's kind of a very interesting result to show that like between 3 different flavors, one oscillates to another. It was not perfect because like this Kamland experiment in Japan, like I think the two sides that you do not have exact distance what you require to have a proper oscillation thing. So, and that's it. So these are the problems which appeared in the say early 90s solar neutrino problem or atmospheric neutrino anomaly with the oscillation and then with MSW effects. These are the more or less picture what we come into. So oscillation we have. Okay, so this is the thing I'm just showing here, 1960 to 2000s. These are the scenario. We know that nu mu oscillates to nu tau, nu e, like from the solar experiment, nu e is oscillating to nu mu and nu tau, and nu e bar from the reactor experiment to nu bar others, and nu mu to from the accelerator experiment also nu mu to other experiment. So now let's enter into the 21st century. Like although some of the discussions involved like early 21st century, but you see, so far we have detected nu e, nu mu, but still nu tau was not detected. Only 2 species of neutrino so far we know. By the time already tau lepton has been discovered, then standard model is there, like it also developed in let's say 60s, 70s. Say, then we know that if there are 3 generations, I should expect some 3rd species of neutrino, which we still have not discovered yet. So then in using some in 2000 donut experiment, it's I think called direct observation of nu tau, tau neutrino basically. That's the name called donut. And there you have 800 GeV proton, and from there you produce this tau, and from the different king like tau decay, you can interpret that you have detected tau neutrino, and donut is the experiment which discover this tau neutrino. So let me summarize. So what was earlier understanding of 20th century, like neutrino is very hard to detect, and how you give the nomenclature of neutrino, that neutrino in the weak eigenstates, whenever it reaches the detector, what type of charge electron it produce, we give that nomenclature, electron neutrino. For the it has some heavier partner, what it's called muon. If you produce muon, then you call it muon neutrino. So that's how you observe. You just did not directly detecting neutrinos. So you are basically looking for charged electrons, and similarly for tau electrons also, you call tau neutrinos. So these are, we give nomenclature flavors. There are 3 flavors of neutrino. And these are the things which I already mentioned, that in 1950s, Newey discovered. Then the second species of neutrino, which I also showed, mu, and in 2000, tau neutrino has been discovered. So far that is our understanding, that it comes in 3 flavors, interact only via weak interaction, have 0 masses. But although I am drawing these 3 things, it was not quite completely correct, because already from the atmospheric neutrino anomaly and solar neutrino problem, we know that it oscillates between 3 different flavors. So you can write down this weak eigenstate in terms of the mass eigenstate. Let me give the nomenclature: nu e, nu mu, nu tau, as I earlier defined. It's in the flavor eigenstate. And nu1, nu2, nu3, those are the physical state which have mass. Okay, you can write down in terms of a 3x3 matrix, and let me call it mostly unitary. By mostly unitary means it's basically unitary matrix, but if it deviates from the unitarity, that will lead to some, it's called neutrino non-standard interaction. Tomorrow I will talk about that. So basically this is the picture which we have now, and there are hundreds of experiments. So far, what is our understanding? I'm just taking from no-fit collaboration. So they basically measures all the mixing angles. Let me write it down here. Like they are measuring all the mixing angles, then Dirac-Sepi phase and 2 mass splitting. And these are measured with few % precision, other than the delta Cp and this normal and inverted ordering. So, and this is called global fit. You take data from different experiments and combine it, and all the neutrino oscillation parameters are precisely measured. And in future also, people will try to measure this type of parameters more precisely. That's what already I showed you. Like so far, our understanding is neutrino 2 oscillates between different flavors, and that's how you wrote. So that means the only satisfactory explanation which you require, that neutrino have non-zero masses and mixing, which is leading to this neutrino oscillation. And in standard model, we know that there is no neutrino mass, because you do not have any right-handed neutrinos. So we need to have some theory. So we know that neutrino oscillates. That means we need also some theory or some theoretical model which can explain these neutrino masses and mixing. And that's also the defined angles precisely measured, like I'm just showing on the timeline. Okay, before going to the other things, let me erase this part. Okay, let me quickly scroll through the other anomaly or other problems which exist in the neutrino sector. So the solar neutrino problem and atmospheric neutrino problem was resolved, but then this is kind of the summary. Still defined experiment look for like different properties, either scattering experiment or oscillation experiment. Still some of the anomalies which are very long standing, it's still not resolved. Say, for example, LSND minibone, and then reactor anomaly and gallium anomaly. I'll just make you aware of this, what it is, why it is called such anomaly and so on, so that even if you can think of how to resolve it, and I'll give some hint like different possibility. So first, before going into the short baseline anomaly, which like last 20 years it was there until 2006, as I showed, all the global fit was quite consistent with all these neutrino oscillation parameter. Until 2006, this LSND experiment, which is in BNL, Los Alamos, it appeared like it was like a liquid scintillator neutrino detector, which was like using 0.8 GeV proton beam and hitting targets, and then you produce nu mu bar, and that oscillates into nu e bar. But what they were finding, that this nu e bar, the LSND detected more nu e bar than the expected. That was called LSND anomaly. This was 3.8 sigma axis during those days. And so community was not believing in it because of the two reasons. Also, like in global fit, this data was not being included due to the fact that because it is in conflict with the standard global fit from defined experiments. There are two different reasons. First, the baseline length was very short, and second, they are only getting such anomaly in the anti-neutrino mode, not in neutrino mode. So it's run like from 1993 to 1998, this at Los Alamos lab. So to test these LSND anomaly, whether that is correct or not, so then a new experiment was commissioned, which was called Minibone. The baseline was like 15 times of LSND, and neutrino beam energy was like 10-20 times of the LSND, and it was had like high statistic like 6 times of the LSND. And let me remind you that these are two different experiments in two different places. It's not like in same place, same problems are occurring. And also in this Minibone experiment, you have this booster beam, it hits target, you produce muon, but there you have magnetic horn where you can produce nu mu as well as nu mu bar. You have control over it. So you have neutrino mode as well as anti-neutrino mode. One different, yeah.
Share this screen.
Oh, okay.
It's sharing. No, sorry.
Okay. So both both like neutrino mode as well as anti-neutrino mode. So you can control over it, and they look for neutrino as well as anti-neutrino mode. And 2018, I think they find like it was like individually like 4.7 sigma axis. And then, as you know, like different articles cover these things, like evidence found for a new fundamental particles, evidence for sterile neutrino by formula experiment, different news outlets covering this news, because it's almost like 20 years old problem. And over the time it grows and grows. And as I discussed in the first stage, neutrino physics history, if you look around, all starts with anomaly, where people are not believing in this type of solar neutrino problem also. So this deficit, which was wrong and so on, it can be experimental uncertainty and all things, but you need to keep, you need to be open-minded. So if something appears, always you try to write down theory which you can lead to. As a theorist, our job is to do that thing. Of course, like you need to be careful while you are considering this, but this is a 20-year-old problem. So it may continue. Maybe there could be some interesting explanation which can lead to this type of accesses. Just if you combine it, it's more than 5 sigma, by the way, if you combine LSND and mini. So it's serious things. And I'll just highlight, if you try to explain this, instead of 3 neutrino, like, so you have suppose 4 species of neutrino. That's the easiest solution you can think of. Like I just showed 4 different cards, but like if you have 4 species of neutrino, which is in the EV scale, then that can oscillate to each other. And with that, you can explain this anomaly. In the past days, people are trying to explain via this thing, but this sterile neutrino at the EV scale presents strong tension between the data set. Also, there are some strong cosmological bounds also are there for the sterile neutrino. And as you see, I am showing here some plot like from the appearance and disappearance data set, this is almost ruled out, where this is the explanation which can lead to this LSND anomaly or Minicourse anomaly. So this is kind of in conflict 4.7 sigma tension between appearance and disappearance data set under the sterile hypothesis. Just I will highlight one of our work with Renata from Sao Paulo and Enrico Pedro, like we wrote down, like there we are explaining this axis. Basically, we are saying that 2e plus e minus, like if you have some like particles like which is decaying, like collimated way, like e plus e minus, and from that it can look like the similar event what Minicourse are looking for. So I'm not going into model detail. I'll explain it later, like why this type of model also can lead to neutrino mass generation, why it's motivated and so on. But the main idea is that in the Cherenkov detector, looking at the track, you can see the fuzziness of the ring. For electron, muon, and photon, it will look different. But the thing that in the water Cherenkov detector, if you have E minus E plus very collimated, you cannot distinguish from the photon type of event. So that was our explanation. And then in the second paper, where we discuss the model, some complete whether any neutrino mass generation mechanism can lead to this type of access, and that's in the second paper which we wrote. And this is in the plane. We are showing these are the experimental constant exist on the mu4 plane. Like if you have 4 species of neutrino, you can write down also 4x4 matrix, which I call mostly unitary matrix. You can write down like that. Same exercise like what you did for the 3 cases. And these are the different sigma significance which can lead to explanation. So the bottom line is that there is still some problems which arise. You can think of something new idea and which can lead to this type of explanation. And then this theory landscape evolved like it's wide. People have written down many papers, defined hypotheses, defined models, and so on. It can come from the sterile neutrino, which is decaying to active neutrino and photon that can lead to this excess. Even if our G prime can be changed with scalar, that can lead to. So there are many evolving landscape, but then microbone also taking data. So microbone first set of results already appeared, and still like this type of topology they are looking for. So the like we are expecting some new result from the microbone collaboration, which maybe can shed light on this type of phenomenon. So of course it's an open problem. So you can think of like still like I'm just giving an idea because if you are interested in neutrino physics, what are the problem also exists, it is good to know. If you want to work on it, so you can come up with some new interesting features. So that's the thing. And then the second problem also, another thing which exists, that's the diabe or the like reactor anti-neutrino anomaly, as you see in the plots, like this type of oscillatory, not oscillatory, like kind of different spectrum they found. And between 4 to 6 MeV, they find some excess of major anti-neutrino events. First by diabe, and then Reno and Double also found this type of fluctuation. And this was not anticipated, but as I mentioned, like there could be different level of uncertainties and so on, and this is not so sigma significance as the LSND or Minicourse. Like that is like almost like if you compared in terms of significance, it's almost like near discovery threshold. But here, like significance is not so high, but still like this is there is like this problem is there, you can think of like what it can lead to. If it can be due to just experimental uncertainty or statistical fluctuation, whatever it is. But this is called the reactor anti-neutrino anomaly. And let me tell you also, this reactor anti-neutrino, this since they put very close within a say kilometer distance, you expect some non-oscillatory behavior there. So this is another anomaly. And the last one which I will tell, which is called gallium anomaly. I already discussed why I was writing the solar neutrino thingy. So there I already mentioned about neutrino and gallium, this gallium and SAGE experiment. This is a radiochemical experiment. And there also some this galaxy and SAGE experiments with radioactive source chromium, which leads to neutrino energy similar to like this. Here I'm just showing this chromium source. When it's captured by electron, you produce μe, and then μe in gallium detector, you then filter out germanium, and that's how you detect. And there was some also defined expectation. As I said, deficit also it was seen by BAST experiment recently. As you see, combined significance or roughly 5 sigma. Again, there could be defined possibility. Maybe in the source, there are some chromium source activities happening, or neutrino detection cross-section of neutrinos on gallium that may be causing this type of deficit, or germanium extraction efficiency was not so quite good. So all these leads to this gallium anomaly. Okay, so then I'm showing you here the next generation detectors, which are now very popular, or like as you see in the neutrino source, the 3 different regions. Like you produce neutrino, these are the source region, and while you create focused point beam and points decays to neutrinos, and then in near detector, you measure unoscillated pattern. But if you allow neutrino to travel a long distance, then you measure like oscillator spectrum, this new, and so on. And there are many experiments ongoing. I'm just highlighting these. So what are the things we are trying to address in upcoming decades? Like what sort of questions we are trying to address? So here I am summarizing. First of all, how do neutrinos get mass? That we still don't know. We solved the solar neutrino problem. We solved the atmospheric neutrino problem, but there we write down just delta M square. But we don't know how this delta M square come from, because in standard model neutrino is massless. So we don't know still. We don't know what is the nature of neutrino. It's Dirac or Majorana. So that's also we don't know. CP violation in the electron sector. That's also this delta CP, like the neutrino program is trying to pinpoint this parameter also. Then, as I said, unitarity of UPMNS, that's also another thing, and absolute mass scale and defined neutrino properties. So these are the major questions which we are trying to address. And I see this problem as like in a 4 segment. Let me try to explain what by 4 segment. Like so far, whatever our understanding is, we know that neutrino has masses and mixing. So then we need to write down theory which can explain neutrino mass and mixing. This is the most robust evidence which strongly demands physics beyond the standard model. It's not in the similar footing in the other like problems, the hierarchy problems or unification or flavor puzzles and so on. These are theoretical like aesthetics problem. But this is based on experimental evidence. You need some theory which requires neutrino masses and mixing. It just cannot pop up like that. And it will have some consequence. So then look at this, what sort of particle or what type of theory you are writing, whether it introduce some new force carrier or new particle, that I call neutrino mass messenger. You can look for that particular particle signature if it is accessible in defined experiment. It can be high scale, it can be low scale, or it can be intermediate scale. You should look for this neutrino mass messenger. That's the second way of looking at it. So now the third segment. Okay, well, there are so many models people propose. How you can look for so many particles, so many defined things. There is another way of looking at it. That is, I know neutrinos, neutrino sources, and I know matter fields which exist in the standard model. I don't care what is inside there. So I will try to look for neutrino, how it interacts with matter, and which we call neutrino non-standard interaction. So I'll not look for a one particular particle or mass messenger. Rather, because this will affect in the oscillation or production. So mostly in the like oscillation thingy. So from there, we'll try to interpret what is the new physics it can lead to. Like, remember that this type of things was quite important because the G Fermi measurement before W and G boson discovery, G Fermi, which is comes from this 4 Fermi theory. Let me write it down maybe. Why this is important? Maybe you already know, but still it's important to point it out. Say, already I wrote down this thing. You started. Now in EFT language, you can write it down like so then compute will be 250 GB. So you see, if you write down this muon decay, say mu minus, it's going to mu, and suppose I'm writing in terms of EFT language. So say electron and mu bar. So and now if I open it up, mu. So this interactions ETF over, say better to write, yeah, √2, and this is W, so it goes like a square, and these couplings are exactly about 2√2. Same thing goes here also. Then you can write down. So experiment look for this type of muon decay, and it plays a pivotal role in understanding of the G, like this construction, what is the W boson mass and G boson mass. And the expectation was like 250 G. It should be below 250 G. If you prescribe in terms of this, these are 4 Fermions operator. Like as you write down, if you compute it, you will see that there should be some force carrier which I should expect. It will be below 250 G. And after that actually in 1980s, anybody knows what experiments discovered the W and G bosons, which got Nobel Prize also later. So it's called UA1 and UA2 experiment in CERN. So, and then interestingly, they found in 1983 discovery of W and G bosons, and which you know the masses. So you see, if you have some guideline, what is this? I'm looking for some process. You can write down in terms of EFT language. Like you know that the new physics scale, which will be involved, that should be below 250 GeV. And later you are finding the same W and G bosons like around 100 GeV, like 80 GeV or 90 GeV. This is amazing. So similar way, what I was trying to tell you, like also later I will discuss why EFT prescription always not good, but you get a very good idea from this muon decay measurement, or this plays a huge role on like predicting some W and G boson mass to be less than 200 GeV, and then you find in 1983, like by these two collaboration, which leads to okay. So that's what I was trying to explain here, that even if you don't know what is new physics involved, you can look for this neutrino non-standard interaction and you try to say that what sort of scale you are expecting whenever you are trying to write down some interactions which generates neutrino mass and mixing. It will generate neutrino non-standard interaction. It will be not only W and G interaction. There will be some interaction will be involved, and that will lead to some effect which you can look for instead of looking at each individual particles which appears in mod. So this is another way of looking at it. Also, like 4 neutrino interaction which you call, if you write down supposing standard model of battlefield, the only operator which is completely unrestricted, or there are some restriction, that is 4 neutrino interaction. There is much more room which can be huge, like even if suppose say Hubble tension and all these things exist, like if you say like it can be 10 to the power 9 times of G Fermi, which leads to Hubble tension. So you can see that like this type of interactions, how important it is to understand what type of theory you are writing down. Okay, so this is the third thing. And the fourth one, which depending on the time, I'll also discuss, like neutrino electromagnetic properties, which is also very robust. Like neutrino mass and neutrino magnetic moment, both are helicity flipping operator. And if you generate, like whenever neutrino mass is 0, so neutrino oscillation demands neutrino mass, and neutrino mass demands neutrino magnetic moment. It's one-to-one correlated. I'll discuss tomorrow. And from there also you can say something about the model or the mechanism which leads to this type of theory. So what does that mean? So people are writing down model or theory which can lead to neutrino masses and mixing. So it can be huge possibilities. So how you can pin down? Maybe look at the neutrino electromagnetic properties which will classify in a certain sector, and also like NSI. Not all models can generate neutrino non-standard interaction. If you discover some, suppose a non-standard neutrino interaction effect, you can easily discriminate many models which cannot lead to. So then if you have an idea of this, these are different way of looking at it. Then if you know that, then you zoom in that particular models of the mechanisms which are very promising, and then look for each individual particle signatures, what it can lead to. So this is the more or less, like in my opinion, like this is the way you should look for, propose some theory, look for neutrino mass messenger, look for some four Fermi interaction, and look for some fundamental properties, and then do like complementarity. Then you will see you can pin down, like you do not need to like deal with millions of models. Just you can easily discriminate, like even if I'll talk about it later tomorrow, that how based on some simple neutrino non-standard interaction, you can classify neutrino mass model in 2 categories. Just one class of model which predicts neutrino non-standard interaction, one class of model which doesn't predict at all neutrino non-standard interaction. So there is nothing good or bad. Just you can discriminate very well. So if you see something or do not see something, you can first categorize those and then zoom in. Okay, I'll not spend too much time on it because now I'll go into the neutrino mass model building things. So as I said, so far what we learned, neutrino standard models are massless. There is no right-handed neutrino. Neutrino flavor oscillation have been firmly established. All 3 mixing angles and 2 mass splitting have been measured with few % precision. And these are the like I showed it multiple times. You write it down. Now what is your job whenever you are writing down neutrino mass model building, or you are writing down some neutrino mass models? So basically, if you have any question, please feel free to ask. So basically in your theory, you write down some Lagrangian, which you can write down, say, M nu ij, because these are 3x3 matrix. So basically your job will be to write down this mass of the neutrino in the Weber eigenstate. Let me explicitly write it down so that so whenever you will write down some model, what basically you needs to reproduce. This is the thing. And this U structure is basically this one. Okay. Which I am showing in the. So basically, no matter what you do in your model, in the Lagrangian interaction terms, what you are writing, that gives this M nu ij structure. Suppose, for example, let me write it down very simplistic way. Say I'm writing down a 3x3 Yukawa matrix. Okay. Say I will write Yij and some heat, suppose say if gets wave, I'm writing down this M nu ij. So you can see the whole structure like basically determined by this Yukawa. Just I'm writing explicitly to just simplify that this is a constant, suppose a number. Suppose that this is not dynamical wave, just a fixed wave. So your job will be to, in your Lagrangian, whenever you are writing, this is your Yukawa. And that's the same PMLS which you are getting from the experiments. So basically, in a way, you need to generate such that that fits your this Yukawa. You understand? So that's the job you are basically doing. You write down some model where you write down this M nu ij term in the interaction eigenstate. And suppose say if you are writing down, I'm just giving one example, but I will classify in different way. But suppose say the Yukawa generates the full structure. This is from the theory which you are getting information, or like you are writing down Yukawa matrix. But from the experiments, I have information from there. So I will fit such a way this Yukawa correctly generates that particular matrix. That's the thing we are doing. Okay. So now the thing is that, of course, as I said, like neutrino has mass, like, but if you see the, say, I'm writing down. Yeah, let me remove this. So you know that in the standard model, suppose say the matter fields other charge lepton masses, how you write down psi L bar, psi R type of term, right? Right. So the simplest possibility you can say, you can just add right-handed neutrino, and you can write down nu L bar, nu R. So, but you need to add this, and if you try to get this Yukawa, so this basically comes from say nu L bar, nu R, say phi, something like that. And when phi is getting wave, you see the Yukawa will be too small. So from electron mass to the top mass, it's a 6 order of magnitude spread. You write down basically m top, say y top times v electroweak, which is 174 GeV. So if you compute y top, it's like order 1. Basically, any Yukawa you can just write in standard model. It's not a prediction, you just fit by Yukawa. So similarly, if you do y electron, same thing you can do. It's like this difference is 10 to the power minus 10 to the 6 order of magnitude in the difference, two different Yukawa. Now, if you go to electron, the neutrino, it's much more suppressed, like 10 to the power minus 12 order or so, which is too small. And that's the thing which I'm showing here. Like it's far from all these charge lepton and quark mass. If you can write down mf over v, this V electroweak, then you can see the Yukawa's prediction for the neutrino, how small it can be. So the thing is that neutrino has mass. That means neutrino, your standard model needs to be extended. Even if at least some right-handed neutrino extension you need to do. There is no other way. And now the question is that neutrino mass models, it can be at defined scales. I'll do the board work. Before that, just I'm giving you the overall idea that these neutrino mass models can be in any scale. It can be high scale, it can be weak scale, or it can be sub-GeV scale. And then also neutrino can be Dirac in nature or Majorana in nature. Depending on defined, like you will have defined predictions, say neutrinoless double beta decay, or say leptogenesis for the Majorana scenario. And then if you have some low scale, then meson decay, charge electron flavor violation, NSI, if your this neutrino mass messenger, what I said, that will have some prediction if it is in the low scale. Yeah.
The fact that the value is that small, people like it is also just a stat. There is nothing that actually forbids that stat.
Yeah, that I will tell you. So even if that's then your 14 GeV inverse, but yeah, I'll tell you, like to get Dirac neutrino mass term, like you need to protect the Majorana mass term, right?
Yes, yes.
And to have impose that, like you need to either impose some, because neutrino is the only particle which qualifies to have Majorana mass term, right? Now, if you impose some global symmetry or local symmetry, there are some issue with it also. Like if you impose some discrete symmetry, that's doesn't respect the gravitational anomaly. So what does that mean? Even if you write down Dirac neutrino mass terms with imposing some discrete symmetry, suppose you do not have any other Majorana mass term, somehow you protect, still at the Planck scale, you will generate a lepton number violating term, which doesn't respect this, because of this discrete symmetry. But of course, there could be some way, if you are doing some gauge symmetry, that you can, a nicer way you can do so that like this, these gravitational corrections can be protected and so on. But there are issues with it also. It's not like completely I'm just writing down. If you adding right-handed neutrino in your theory, always you can write down the Majorana mass term. Okay. So, and there is no problem. So that's why even if like, if it is purely Dirac type, like even if say it predicts some, suppose a magnetic moment, which I'll discuss, which has some interesting feature, even if like whether it comes from defined way of looking at it. Maybe I cannot probe this Yukawa nowhere, this 10 to the minus 12, but nature has very high magnetic field. In some cases, it can be maybe sensitive. We need to just come up with some new idea. And as you see that, like always it was a like almost impossible task. Even if Pauli is writing that it can never be detected. In 30 years, how the technology developed, you cannot expect what is going to happen. So, like we need to be optimistic. And even if it is a like pure Dirac type of particle, there are other places, some clever way to look around it. So, yeah, I'll discuss some of these aspects, but that's a very good question. So here, just the main summary is that even if it is high scale, like very high scale, say guard scale, then also you will have some predictions, like for what Kamiokande experiment was built, suppose from it comes from some grand unified theory, you will have some nucleon decay expectation. So proton decay or something, even if with the some rules it's correlated. And if it is in weak scale, intermediate scale, suppose if it is collider accessible, all these particles, then you see some signature. So you will have some defined kind of expectation in defined scales. So you need to be just open-minded. Okay, now I will discuss these things. First, let me write it down. The standard model things. And now I will explain how to construct neutrino mass models from the scratch. Yeah, you have spray so that like spray the liquid, if you spray, it will be completely clean.
I don't know, you want me to ask me?
Yeah, maybe you can go. Yeah, if you have any questions so far, what I have discussed, now I will first talk about Majorana neutrino mass model building. First, I will tell about tree-level seesaw and like tree-level models, and then how to get in quantum loop corrections. These are the two categories. Even in quantum loop correction, then I'll tell two approaches. You can do operator-based approach, and you can do graphical approach. So that I will like give hand to hand these how to do that. So that you can at least learn if some problem arises or how to write down a Lagrangian, and from there you can come up with some neutrino mass models. And then in the second section, I will talk about how to do same thing for Dirac neutrino. Whatever Gustavo asked, suppose say, like even if on the simple tree level to loop level, what sort of things we can expect.
Slide, I was curious about one thing. There was no immediate consequence of the Dirac cluster, right?
Yeah.
So it seems that most of the time when we're looking for a Dirac nature of the neutrinos, we're basically ruling out the Majorana nature instead of using Dirac for Dirac nature. Do you know, are you aware of any problem of Dirac nature by itself without ruling out the Majorana term?
No, there is nothing ruling out. Like there are two possibilities, as you said, between Gustavo asked a similar questions. Like as I said, in the Planck scale, it depends. Like in theory, you can always write down Majorana mass. It's not protected. Neutrino qualify for that. No any other charge fermions qualify for this type of like Majorana mass terms. Because like either you need to break the electromagnetic invariance, like you cannot write ML plus. So for neutrino you can do that. So always whenever you are writing down theory, always you can have Majorana as well as Dirac mass terms. It's unprotected. Now suppose say you say that neutrino is completely Dirac. Also it is possible. But my take on this is like since it's allowed, like ask this question, like why is Majorana mass term will be protected? That means you are imposing some symmetry or something which makes it real. So then people come up with some either some discrete symmetry or some say gauge that symmetry. You are imposing discrete symmetry. There are some papers where it is shown that if you are imposing discrete symmetry, that doesn't respect this gravitational paradox, which leads to this electronormal violating terms at the Planck scale. So at the end of the day, you will get some pseudo Dirac type of nature, not purely Dirac. But if you are gauging it, like if you impose some local symmetry, that maybe you can get some purely Dirac nature. I will explain these things. That just the first segment, I will discuss about how to get Majorana neutrinos, but then I will discuss about what you are saying, like how you can come up with some symmetry for your neutrino is purely Dirac. You can motivate it this way because we are looking for neutrinos double beta decay. We are not finding any. Maybe neutrinos are Dirac nature. How to get that? What is the argument behind this? Why? Maybe you can explain the smallness of the Yukawa and so on. Let's go into that. So,
Very soon we are having a coffee break.
yeah.
We are just waiting for the next.
I think we're right.
Yeah, so we'll decide when to stop.
Yeah, I'll maybe let's proceed a bit up to say tree level Majorana mass. I will finish there,
Then
and then we'll go to break because then the radiating part I will explain that requires some attention. So it will be good to have some break. So let me finish it. I will quickly finish this part. I will not get any spray.
easy, you for it to break.
Okay, I see. So
So maybe you gonna use it for right?
this thing, yes. But the camera
Just in the yeah.
Okay, let me first write it down something.
Yeah, that's it.
So this will be our starting point. And I will not erase this because I need it every time. So I think already you are aware, but how to write down a operator which is electron number violating or conserving, whatever I require. These are the standard charges in all these are standard model fermions. So this is the lepton which you write down like nu alpha, L alpha, and this is the say right-handed type of electron, which these are the charges. So these means like, let me just tell so that nobody miss any point. And if you have some doubt, you can ask always. So these are colorless. One means colorless particle. The quarks colored 3. Okay. So this is conjugate particle. So that's why I'm writing 3 bar. And so and H is like this is standard model Higgs, which is colorless again. And the second charge is the SU12 charges because the leptons comes as a doublet, the left-handed leptons. And then the right-handed electron is the singlet because in standard model you write down it as a singlet. And the quark also left-handed quarks, it comes as a doublet, Higgs as a doublet. So you can see that SU12 charges, and these are the hypercharges. And you need to keep track of this. And hypercharge, how you write Q I3 plus Y, you can compute like how you can get the charges also properly, right? Suppose for neutrino. So this is 0, half minus half 0. And then the like minus half is -1. So this already you know, just I'm telling that this will be very essential, how to write down an operator and so on. So keep track of all these charges. Okay, so neutrino mass in the standard model is like neutrino mass is 0 basically. Here, what is our conclusion? Neutrino mass is exactly 0. So the next question you can ask yourself, okay, that what I can write down which leads to neutrino mass. Neutrino mass means like I need at least L and L, that type of term. With these charges, what is the simplest? I will not add. So for the moment, let's think about this thing. I will not add any particle into the standard model. Okay. So if I do not add any particle, if I take the EFT approach, what is the simplest possibility I can write down for neutrino mass? So I cannot write down any dimension for term because you see L whenever you are writing, and also keep track always fermion dimension 3/2 and scalar dimension is 1. So just writing down so that you do not forget, because it will be also essential. So you need to write LL because whenever you write down mass of the neutrino, like there should be two neutrino field, right? So that means you need to write down 2L. It's a doublet, it's a doublet. So to write a gauge invariant operator, what you need? This is a colorless particle. With these fields, what is the simplest possible operator or the minimal operator you can write down? The simplest one will be, as you see, H is half, L is minus half. The simplest operator you can write down LLHH. Because doublet will contract. I cannot just write, okay, for the moment, just I cannot, sorry. I cannot write down just H. It is not gauge invariant, right? So I need another H at least. Okay. Then whenever these two Higgs will get waves, V square, I can write down something like these two neutrino mass term because these are constant quantity. Sorry, I'm repeating it. Some U power times this. So this is the simplest operator you can write down with the standard model fields, which is known as Weinberg operator. This is the dimension 5 operator you can write down. You cannot write down any other operator below this. Okay. And this will be lambda nu physics. And if you this is proposed by Weinberg in 1979. I'll also share the screen. Yeah, that's what also I'm writing here. That if you write down, it's the proper flavor indices and other things you are writing down. So this is the EFT approach. This is the minimal dimension operator you can write down, which like lepton number violating and which can generate neutrino mass. Okay. Based on this, you can see that LLHH, like you can see like this, minus half, 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 that cancels out. And also this is doublet, doublet contract, doublet contract. Okay, now let's look at the possibility, how I can open it up, okay? So my job is to, like you have operator like this. Another thing I want to mention before proceeding, you should give arrow properly. Drawing Feynman diagram, if you know correctly, you can, like half of the problem will be solved. And if you don't know how to give arrow, you will be, every time you are trying to see some models or the things, like you will be confused. Be clear when you write down new L, new R, always it's this type of mass terms. If you are writing Dirac type of mass terms, you generally write like this way. But whenever you are to show the lepton number flow, but whenever you are writing down Majorana mass term, let's do this. For the Majorana case, you will have either two are going away or two are coming towards inside. You need to keep in mind always. This is for the Majorana cases. So, okay, because that shows that it's giving the delta L equals to 2. And here lepton number entering and which is going out. Just to keep in mind all the basic tools, whatever you need, and just writing it down. So now see this LLHH operator. Let's try to open it up. So you have L, as I just clearly tell you, I'm now talking about 3-level Majorana mass model. So let's think about two arrows are going inside, okay? Two arrows are going inside. I'm writing down LL, which is from this operator. Now, there will be 2H, because that's the operator I write now. You can clearly see the arrow of the H will be towards going towards this one, because you see minus half is going in, minus half is going in, and H has hypercharge half. So like it will compensate, half is going inside, half is going inside. Okay. So now I'm telling from very basics, okay, so that you can follow these things. So now whenever H gets a wave, this is basically the mass term, because that's how you write down mass term, right? So the L means always neutrino, which resides in here. So you can write down, say, I'm not expanding this term, this is a Majorana mass term you are writing down, suppose say this type of term. Okay.
Arrow on the H is L, arrow on the L is with carbon. On the H.
This is a scalar, Higgs field. It's getting to here. Just to do the this arrow defines the hypercharge.
All this arrow represent.
Yeah. Like arrow defines everything. As I said, in Feynman diagram, whenever you are writing down any case theory, like under any, say, in standard model, you are writing down neutrino masses. Like you need to abide by many things, right? Dimensionality, the three defined gauge invariance, hypercharge. But one of these is hypercharge. So I need to take into care. This is just one of them. Yeah. For the for the Higgs field, you are right. For the Higgs field here, I'm showing the arrow to keep track of the hypercharge. Yeah, because it's colorless particle, so it's very easy. That from this charge, I do not need to think too much. Okay. But from here, doublet, that's also contracts, because doublet gives, like I'll open it up. But the hypercharge, that is defining the arrow. Okay. So whenever these two Higgs field will get wave, like basically you can write down some, say V electroweak square over, suppose this is the lambda nu physics. So it will be like this. You understand? Okay. So now let's see if this is a minimal possible operator, how you get to different type of neutrino mass models. This is very simple. Depending on, you have four field. Just depending on which field I'm contracting with what, that will give a new model. Okay, let's work out. So suppose say I have LLHH operator. I'm not writing down anything else. I can do either LL contraction, HH contraction, or I can do LH contraction, LH contraction. How you are grouping these two fields. Okay. So let's work out this one. How it can lead to type 1C. So suppose say you are in the like early 21st century. You try, or like in the late in the late 19th century or something like that. You try to construct some neutrino mass model from this Weinberg operator. How you can do that? So this L and H. So let's draw the operator. I will just open up this block. That is my job, and that will lead to defined model. So as I said, L direction, that's what I'm drawing it here. Now I'm contracting L and H. That means in one vertex, I always write H, which is going towards this direction, and H going towards this direction. Okay. I don't know what new particle I need. Now I'll ask you guys. So this is L and H. How you can like contract. This is a dimension 3/2. This is a dimension 1 term, as you saw, and that's why I was writing down. So if you're writing down a particle, so suppose that there will be new particle, right? Here it will be a new particle, because in standard model there is no particle which is contracting L and H. So what should be its nature? It should be Fermion, because dimension 3/2, whenever you are starting with a Fermion, it should be another Fermion. Okay, I know that I require a Fermion. Now this is doublet. Higgs is also doublet in standard model. So doublet, how it can contract? Doublet gives triplet, SU12 triplet or singlet. So I know that these particles, SU2L charges should be either triplet or singlet in nature. Did you get that, or you cannot keep track? So I know this will be Fermion. I know this will be colorless particle because let's look at all the. So SU3 color charge, it doesn't have, so I do not have, I should not have any like color particle here. Now SU2L charges, this is doublet, so it can contract like 2, it gives like 3 plus 1, singlet or triplet, either it can be singlet or triplet. Now, okay. So if I know that, so now from the hypercharge, let's take a look. Minus half, it's 0. It's hypercharge should be 0. So now you can write down, say, Mn, Nr, Nr, and that is completing the diagram. So if it is singleted nature, then we call it type 1 seesaw. Okay. And in like, that's the simplest example you can think of. And then if it is triplet, so if it is singlet, this is type 1 seesaw, we called it, because there then neutrino mass will be basically, you can write down, the Mn, this is in well in our basis suppose writing, then your active mass matrix will be something like the electroweak square, because square over Mn, or whatever you are writing down here. So that's the type 1 seesaw, how you did that. Then if you go to triplet scenario, as I said, it can be both nature, SU12 singlet or triplet. Triplet, if it is, it's nothing different. It will be just called, give the nomenclature type 3 seesaw, because there you expect, since it is triplet, there should be some charged fermion. But the main like idea is similar. Now, let's take a look of this operator. Like, okay, I just said that if you are contracting L and H, now think about, I will contract L and L. Again, give the arrow properly. You are writing down Majorana mass terms. Either it will go towards the vertex or both should go away. So if it is L and L contracting, what should be the new particle's nature in the renormalizable way? So it should be scalar, right? I'm losing already dimension 3. So only I have left, I can write down a dimension 4 term. So it must be scalar. Okay, I know it's a scalar. Now it's a doublet, again, this is colorless particle, so it should be colorless. Like, look at the symmetry, and then doublet contracts with a triplet. So you can write down a scalar, and that again goes to H and H. Okay. So if you have a SU2L triplet scalar, and that is called the type 2 seesaw. So that's how you can open up this dimension 5 term and write down a new model just based on that. And here your neutrino mass will be basically the same thing, like Y and V delta. If it is getting some induced wave, you can write it down, and V delta will be V electroweak square over M delta, something like that. Okay. So you can see for the neutrino masses, always the new particle which is involved, that comes into the denominator. If you go higher and higher scale, your neutrino mass will be too suppressed. So that's how you generate a light neutrino mass term. So far everything is clear, because when I will go to dimension 7 terms, dimension 7 operator, it will be cluttered. So good to keep track this simple scenario. These are maybe some of you already know, but don't be upset just because I'm telling again these things. So You have some question?
Can we go for upgrade now?
Yeah. we will. Yeah.
So this scalar can be similar or different.
Yeah, there is some problem. I'll tell you. Yeah.
Combinations, other dynamics, we have to. Doesn't have this.
Yeah.
And I think this. Yes, but the other end of that is scaling options.
Yeah, that's it. That's it. Even something. Yeah, yeah, no, but taking that one, determined here because of the scalar. QB coupling is allowed. So that you can, but you are right. So, yeah, so because here you do not have any other option. Whenever you write down two fermion already, and that you need to write because two neutrinos are there. So then there is no other option. So here I can have, I'll show also that not only QB coupling, it can be comes from verticals. Like I'll show you how it leads to some higher dimensional operations.
And then I'm asking will be dimension.
Yeah, yeah.
We can talk about this.
Yes.
Just about this latest paper by me now that might be like.
I'll talk about that also.
Okay.
Yeah, but you will just tell me when I need to start.
I think that. It was cold.
So when I can start. Oh, already a question. Maybe ask you. Already started. I'm here.
So when we go on the release, it was get that. No.
You can see that the same dimension 5 operator, and if you compute that the scale involved, like from the muon decay, as I said, like you are expecting some new physics scale below 250 GeV. So from the neutrino mass point of view, you can see that that scale is 10 to the 14 GeV. So and also then like why there are strong motivations also to go beyond EFT. Sometimes EFT description cannot be the end goal. because if neutrinos are Dirac particles, then the operator I just write down LLHH dimension 5, that's not the correct prescription, right? And then also if your neutrino mass Ri is higher than like dimension 7 and dimension 9 operators or higher dimensional operator, it can also maybe not, it should not go through the dimension 5, then the scale expectation is different. I'll tell you that also. Just one thing to mention that unlike the quark, if you see the CKM, like all diagonal entries are almost like 1. Off diagonals are 0. And that if you see the PMNS structure is quite like mixed. If you see the diagonals one, not like close to 1. It's not like the CKM things. So that's what you need to generate in your neutrino mass models, which I already have discussed. And I already discussed, I show to you like how in tree level you can have defined realization of LLHH operator. And then if you H and 2 hex is getting there, it's basically the neutrino mass. That's the standard seesaw mechanism, how it's called. I'm just briefly giving the overview. And then type 1 seesaw, whenever right-handed neutrino is a C12 singlet, that's the type 1. Type 2, when it is a C12 triplet, I already discussed. And then the type 3 seesaw, when you have a C12 triplet. Okay. And there is an independent mechanism in general, which are called radiative mechanism or neutrino mass. Generally, you get through the quantum loop correction. And tree level, you cannot, due to some either particle representation or due to some symmetry, you cannot write down lepton number violating term in the tree level Lagrangian. And also, this type of theory quite often do not require any right-handed neutrino. You do not require any matter spectrum like matter field extension. With just scalar extension, you can do that. I'll tell you in detail. But before going to that, also some features I should mention, which are like I already discussed this type of model, how to expand it, LLHH, and you write down generally this type of Dirac mass term. So you see LHH is conjugate, this type of term, and then one mass term, which you are writing, these are the two terms. Then you can write down, and from this F nu, you generate the Dirac mass terms, and MR, which is this term, then you can write down neutrino mass like M Dirac square over MR. And that's the expectation. I should mention, I think somebody was asking, like in nu L and nu R, you have basically 3 nu L and 3 nu R, right? Now, if you say MR to be 0, basically, although you have 6 fields, you end up with basically 3 physical fields. Nu R has no separate mass, it's not sterile neutrino. It's just the counterpart of nu L, like unlike similar to the charged leptons and charged fermions. But whenever this MR is too heavy, then again you have 3 light neutrinos and 3 heavy neutrinos. You have 6 species, 6 physical neutrinos. And if it is too small, suppose say the correction happening at the Planck scale and so on, then still you have 6 species, but the splitting is too tiny. So then these are sometimes you give the nomenclature pseudo Dirac type of scenario. Okay, so here this type of expectation is like this in the good thing about this also right-handed neutrino extension, like it comes with some many other interesting problems also you can address. Suppose say N being a Majorana fermion, it can decay to L plus H and L bar and H star. Also, it can lead to some lepton asymmetry, and you can explain leptogenesis. I'm not going in detail of these things, just I'm mentioning it to you, like just adding right-handed neutrino, not only explain the neutrino mass, which we already like neutrino oscillation discovery, neutrino oscillation discovered, we can explain that, as well as like some matter-antimatter asymmetry of the universe also can be explained via this type of seesaw mechanism. But of course, there is kind of one thing that everybody has their own favorite version. Okay, it can be high scale, it can be intermediate scale, it can be low scale, how the Dirac Yukawa texture looks like, and so on. So here I'm just giving some summary. Sometimes like these are good to take a look. Like there is a upper bound for M. If you you are not taking say perturbativity limit and so on, this is the limit. You can write it down from the hierarchical problem hint. If you think that hierarchy problem is real issue, so there also there are some papers on that, because whenever you are writing LHN coupling, that also gives the Higgs mass correction. Okay, and that also you need to take into account, and in this type of CASA's paper and so on, this type of limits are 10⁷ G. If you think that's a, like if you are treating like Higgs mass hierarchy problem and so on, so then you need to take into account seriously this type of things. But it depending on the theoretical aesthetics what you are taking. And then leptogenesis, for vanilla leptogenesis requires to be greater than 10⁹ GeV. If you see something, some numbers are less than something, so all cannot be solved simultaneously, right? So everything has its own version. So depending on which one you are trying to tackle, like it can lead to different phenomena and so on, and there could be different versions. And I already mentioned also these things, this type 2 seesaw, the same idea, like this delta gets induced wave whenever the electric symmetry is broken. Like this delta gets, if you start with a positive mass square term, it gets some developed wave. Basically, you write down Yukawa times wave of delta. And this Yukawa generates the, like in the beginning when I was telling, this Yukawa generating the flavor structure. Like the all these neutrino oscillation observables. I'm not going in detail. And then the type 3 also, the same thing, but just with triplet fermions. Then you write down this Majorana mass term. And then the one thing is that you will have some charged fermion. Other than the standard model charged leptons, there will be some PSM charged fermions, which is the expectation of this type of model. So that's it. And then I will tell like a very another like counter example, how to like not necessarily you require 10⁻14 GeV. Suppose there are grand unified theory which like in SO10 and so on, it demands there should be right-handed neutrino scale 10⁻14 GeV, everything very goes well. But like also there could be other motivations. Suppose it's phenomenologically testable scenario. This inverse seesaw scenarios also, it can be interesting because it's sometimes called bent seesaw. Instead of 2 field, you have 3 field. But I should mention that in literature, fast neutrino mass generation appears in inverse seesaw, not in type 1 seesaw. But during those days, people don't know that neutrino has mass or this oscillation phenomena is there. So people try to write down how to cancel down, like in the, I think first paper, it was in the footnote, how to get a 0 neutrino mass, because that time you are not aware of the neutrino gets mass and so on. So this inverse seesaw, if you see the structure, this third entry, which is lepton number, the diagonal entries are the lepton number violating terms in this basis. And if by ad hoc, people generally take it KV scale. Earlier, like you see, like M Dirac square over MR, but here you have a new term, which is mu, proportional to mu. If you take it to be very small, then the new physics scale, this you see the structure, this MR scale can be very light, okay, depending on the mu scale. So your new physics scale can be bring down to some lower scale, even if some TeV scale and so on. That's what I am showing it here. It's sometimes called bent seesaw. If you take even in order of 1 Yukawa, even in TeV scale, this inverse seesaw can be realized. I'm just not going in detail because I'll show some other model construction, but if you have some questions, you can ask me and so on. And here I'm just showing one interesting thing. If you see the mu scale, if you push it higher and higher, like in dark scale and so on, it's behave as a like Majorana particle. But whenever you're pushing this mu to be very light and light, it slowly in all, suppose say all the collider and everywhere, it will behave like a pseudo Dirac. Because if it is small, lepton number violation is too small, you will not see any lepton number violating signal in colliders or in experiments. It will behave as like a pseudo Dirac fermion. Okay, and that's what it is showing here. And if you push this mu scales to be 10 to the 14 GeV, that's basically type 1 seesaw. You can integrate out, the other things will be appeared as like type 1 seesaw. But whenever you are going down mu to be lighter scale, it's kind of quasi-Dirac type scenario. So that's how you bring down the new physics scales to be light. I will give you another example. As in the first slide I show that if we are optimistic, this new physics scale can be anywhere, heavy, intermediate, light. Think about how to get a neutrino mass generation even below electroweak scale, because there are so many neutrino experiments are upcoming. If it can happen, right? Like lepton number violation happening at the very low scale. Still, you can suppose then if it is true, then if you have magnetized detector where you can distinguish the charge of the lepton, so then you will expect some signals in this neutrino experiment. And how you can build such model where the new physics scale can be light. Okay, there are two possible ways. Either you go to higher dimensional operator, you need to make sure that lower dimensional operators are not generated, and you are generating neutrino mass by higher dimensional operator, or it's getting via radiatively or quantum loop correction, because then you will have extra chirality suppression as well as loop suppression that will push down some new physics scales to be light. Let's see this example. You will write down, as I just worked out the minimal dimensional operator, LLHH operator, which I worked out. Then even if you can write down some higher dimensional operator, right? And if you write in terms of EFT language, this expression exactly doesn't like it will be not correct. But if you make it say light scale new physics, then it could be more complicated than what I write down. But effectively, you see that this is V electroweak scale, and this 1/16 pi square. Each time you have one loop, then you will have this n will be 1. If you go into two loop, n will be 2. And if it is 3 level, n is 0. Basically, that factor is not there. And this d is the dimension. If you are going higher and higher dimension, then you can see that the new physics scale can be more and more suppressed. Let me explain this graph. So suppose that this new physics scale, which is generating neutrino mass, and this is the different dimensional operator, which starts from dimension 5. Okay. So if you start with dimension 5, let's see, look at the tree level, like which I just wrote it down. 10 to the power 14 GeV, I am having suppose you in the range 1 to 10 to the minus 2. I just want to show the effect. If the dimension 5 operator, you are going to one loop level, then there will be extra suppression. So the new physics scale can be much lighter, almost 2 orders of magnitude below. Then if you go to two loop, it can be 4 orders of magnitude lighter. So, and LHC accessible range is here, late here, and if below, then any neutrino experiments or low energy experiment, somewhere it will show up, if it is like that, okay? So if you see the dimension 5 operator, lowest possible operator, if you write down, that's how the scenario is. If you go to dimension 7, as I said in this term, if dimension is more than 5, so then you are getting more suppression. From 10 to the power 14 GeV to you are dropping down to 10 to the power 6 GeV. Okay, if you are generating dimensions, neutrino mass via dimension 7 operator. Similar way, 1 loop, 2 loop, 3 loop, you will be more and more suppressed. If you go to higher and higher dimensional operator, that's the case. Okay, so the takeaway message is that it can be at different scale. So, like it doesn't need to be at the TV scale. Collider was there, that's why people are trying to write down in the TV scale. It can be in the say sub GeV scale. Neutrino experiments are upcoming, anything, anywhere it can show up and so on. So that's the main idea, just to give an overview that how people can do that. And then quickly I will give one example. So then you can ask me that how you can generate this in 3 level higher dimensional operator. This is also similar idea we'll take. So the simplest example operator you can write down, say I wrote down LLHH, right? That's the dimension 5 operator. Now H dagger H is singlet under any any symmetry. Okay, so h dagger h I always can write down on top of this dimension 5, and it becomes dimension 7, and then it will be lambda cube. So then your new physics scale can be dropped. Now let's take a look at the simplest possible, like simplest model you can propose out of this. These are sometimes called BNT model, Babu Nandi Tapatal. But this is very simple. Like anyway, I need to get 2L. So let's do 2L. Similar way. There will be much spike of Higgs. So L, let's start with L. And I'll do H contraction. So I need to have 4 H and 1 H dagger. Okay. So how I can do that? Let me. So you see, like I can have suppose I am doing this type of contraction, L and H in one side and others are on the other side. Okay. So you see that this is doublet, this is doublet, this is doublet. So isospin 3/2, right? So I need a particle which has an isospin 3/2. That means I need a quadruplet. Okay. You see the operator, follow the operator again. L, H, H dagger H. Okay. So if you are contracting these 3H, only you can go via a quadruplet. Isospin half, isospin half, isospin half, 3/2, that can be only cancelled out with isospin 3/2 particle. Okay. So this is a quadruplet which can consist of, say, like similar to the type 2 seesaw scenario, you can have some this type of particle. Just I am giving you one example how you can construct that. Now you see the nature. This is isospin 3/2. This is this is quadruplet. This is doublet. Then what can be its nature? It should be a fermion. That's quite obvious. And it should be triplet. That way you can only contract. So I know that now there will be only one particle, like some sigma or some fermion, which should have like triplet fermion it should be. Because from this side, you can say that I can do LH contraction with a singlet or triplet, as I earlier mentioned, right? So, but from this side, I can see that I need to have a triplet. So now, if they have Majorana mass term, so basically you are generating H dagger H operator via this, and that's the simplest model of dimension 7 at the tree level. I just want to give an overview. Just don't be puzzled that like you can do it systematically. Just take the minimal approach. Like how I can contract, I should extend the particle spectrum as minimal as possible. If I am writing down this operator, how I can do that. So then just follow the principle of gauge invariance and other things, then you can come up with this type of model. Okay, I'm not going in detail of this. So tree level, more or less, that's it. And then you can just continue similar things for the higher dimensional operators. I'll give you some example that why these things are interesting. Yeah, I'm not going in detail. Another thing I want to mention, which I wrote with Renata and Pedro, like that's also similar sort of idea. Like where we are generating via dimension 9 operator instead of like dimension 7, we are generating via dimension 9 operator. I'm not going in detail. Similarly, LL, and there will be such a way you will write down this is dimension 3, 4, 5, 6, 7, 8, 9. Effectively, like you can write down such operator. Then what will happen? Your new physics scale, everything below the electroweak scale, it automatically comes. Okay. And the structure is following, like I saw the inverse seesaw structure. Generally, yeah, this is the structure. So this mu generally people by ad hoc take it to be KV scale. Okay. Now, suppose say I assign some charge to this L prime, then you cannot write down this term. We are asking this question whether you can generate it dynamically. Okay. So if you are writing down some assigning some charge, I cannot just write down bare mass term. Okay. And then if you introduce some particle which carries some 2 unit of lepton number, although you cannot write down bare mass term, you can write down some terms like with S2 which has a 2 unit of lepton number. And this is anomaly free. Suppose say under some U1, you can assign +1 and -1 unit of charge, which is anomaly free. And then this S2, suppose say in the potential, you start with a positive mass square term. It will develop some wave whenever the electrolytic symmetry is breaking and this U1 is broken. So S2 will get wave if you have this new symmetry which is protecting this term to write down the mu term. That will be generated like similar to the type 2 seesaw cases, like where you get some induced wave. And you can see that it can be very small. And if it is very small, if you look at this 3 by 3 mass matrix, playing in Mathematica, you will clearly see that if suppose say you decouple this 1, 2, and 2, 1 Dirac mass term to be very small, like from the electroic symmetry breaking. Generally, we take Dirac mass term from electroic symmetry breaking when standard model Higgs gets some wave. But when this any charge, you cannot write down with the standard model Higgs. But you can write down with some phi1, some new scalar, which assigning charge such a way that you can write down such term. Now, if you push that scale to be very low, if you push just even if forget about neutrino mass, just look at the 3 by 3 matrix. This 1, 2, 2, 1 entry, if it is small, you will see that that M scale will be very light. If you try to generate the neutrino mass, say EV scale, if you can bring in more and more lower scale, this M scale will be lighter. That means the new physics scale involved will be very light scale. That's in other way already we discussed, right? If it is dimension 9 operator, like this new physics scale will be suppressed. That's how it is happening, and this gives the right way also explaining the dynamical origin of this type of mu term to be why is to be KV scale and so on. And as I said, if you have this such type of models, immediate there will be some consequence in the neutrino experiment and so on, and which we find like immediately like some sort of signature like in mini bone, suppose say, it can lead to some collimated E plus E minus signal and so on. So I'm not going in detail. Now let's start the radiative model. I give you one example that where neutrino mass scale can be lighter but while you are generating neutrino mass via higher dimensional operator. There is another approach you can take, like if you have neutrino mass is generated via loop level. And whenever you have loop level you are generating, there is 2 suppressions you are automatically getting. As you see, there will be a chirality suppression if you are going through the standard model charge leptons or quarks, and there will be extra loop suppression. I'll explain in detail. And another thing I should mention, this is the standard seesaw operator, which I also write it down here. This is in the tree level, but there is a possibility that in model, suppose you do not have any fermion extension in compared to the standard model. I do not introduce any right-handed neutrino or anything. Still, I can write down delta L equals to 2 selection rule. So I need to generate neutrino Majorana mass of neutrino, then I can write down delta L equals to 2 selection rule. Based on this scale invariance, you have quarks and charge leptons and all these things. Basically, you can write down all possible operators. Okay, so this is in dimension 5, and these are all in dimension 7. You can write down such operators. You can same task you can do for dimension 9 and so on. And these are finite possibilities. Okay, so why I'm saying dimension 7? Like let's take a look. Dimension 3, dimension 4. Sorry, so dimension 3, 6, 7. Yeah, so like 2 fermion dimension 3, 3, 3, 1. You understand setup. And if you see the contraction, like you will see that it's perfectly goes well. If you have 3L and 1 EC and 1 H, it's contract. Even if you can do with the quarks also, the same thing. Like basically Li, Lj, say Li, Lj, two things, Qk, Dc. I will explain it. I expand it so that you can understand what I'm trying to say. Don't be lost. But you can write down in a systematic way all these delta L equals to 2 operators with the standard model fields. I have no assumptions of any new fields or anything. With that, you can write down finite possible operators, which you can write it down. Okay. And that was first written by Babu and Leung in 2003. I think they missed some operators. They missed one operator basically. In the Gubia and Jenskins papers, this all singlet operator were introduced and some phenomenology had been discussed. And recently in 2017, I think this Holkas et al. Melbourne group also discussed about all these possibilities. And then recently, me with Babu, Gopal and Anik, like, because there are so many possibilities, we categorize these radiative models in just two simple categories. And based on some very basic principle. What is that? We called it, gives the nomenclature type 1 and type 2 radiative mechanism. Type 1, a mechanism which we are giving that inside the loop, there should be at least a standard model particle. Okay. If it is there, this is a finite possibility. This is not infinite possibility. You can follow this basic principle and you can cut down these operators and write down these operator very nicely. And I'll show you how what do I mean by cut down these operators. I'll explain it in board. And these are called type 1 radiative models. And if you have type 1 radiative model, generally standard model fermions or some standard model Higgs will be inside, and then it will generate NSI automatically in a significant level. Classic example is G Babu model or G model. But then there is a second category where if you see there is no particle inside the loop is standard model. These we call it type 2 radiative models because there you have infinite possibility because all particles are BSM particles. You can do whatever you want, like explain many particles and do charge assignment such a way because it doesn't follow anything. So there is nothing good or bad, but this type of model can never predict any NSI. It will be super suppressed. So classic example is this scotogenic model, which is proposed first by Zhijian Tao, and then also independently after 10 years also Ernest Ma wrote, but recently we just find out that this model is first proposed by Zhijian Tao in 90s. And Ma also did the same thing, this scotogenic model where you impose some discrete symmetry and if you all the particle inside the loop, some dark matter also you can achieve and so on. These we call type 2 radiative models. Now, let's take a look, like how I can, it looks so far complicated, right? How I should keep track and so on. It's maybe complicated. If I work out, I think one thing you will clearly can follow, how I can come up with
Going to take too long these.
Yeah.
Maybe it's impossible for tomorrow also because the guy so he said he has to leave. So I told him till 4:30. He said you can take 4 minutes, but
okay, maybe 10-15 minutes.
15 minutes is
Yeah, 10-15 minutes I will stop and then maybe I'll continue from there. Okay. So let me just quickly give one example to give an idea. So suppose the simplest model, one of the simplest model we call it G model. But how G arise to? It's kind of random particle I should introduce, or there is some systematic way of looking at it. Okay, let's take a look. So whenever you are talking about, I'm there or the screen is there? Okay, so let's talk about radiating neutrino mass models. Mass mechanisms. Well, so radiative mass mechanism, I am preventing dimensions 5 term at the tree level, either due to particle representation, as I said, or due to some symmetry. You are not writing down any tree level mass terms. So the simplest operator, let's work out this one, the simplest one, suppose say. One example, if I can work out, then you can do the other thing, whatever you want. Let's take a look. So if you see the operator, suppose let's focus on this particular operator. I'll not do too much. So you can write down this dimension 7 operator, right? So this is following this delta L equals to 2 selection. Now, you can write down in a two-way. So L, ECH. I'm not writing all these indices and so on. And I can do also another thing, LL, LEC, and H. So the way I explained it to you earlier also, that how you are contracting an operator, even if LLHH, I showed you that whether you are contracting with LL or LH, that leads to a new model. Okay. Similarly, I have this dimension of 7 operator, and suppose I can write down in two form. Let's call it O2A and let's call it O2B. So what does that mean? Suppose let's work out this one. I'm contracting LL. So simply write LL. Okay. And I'm contracting LEC. LEC. All these are standard model field. Sorry. LEC. And I will have H somewhere. Now the BSM particle which you are introducing, say LL, what should be its nature? Scalar. This is dimension 3 is gone. Like for the neutrino mass, at least you need to write LL. There is no other way. So let's write down a scalar. And the colored one as the BSM particles. Okay. Now LEC, that also will be scalar. Okay. How you can write it down. Now let's look at what will be its nature. LEC. LEC means, look at this. Colorless, colorless. So this particle's nature should be colorless. Now let's take a look. Doublet, singlet. Then I need a doublet. Do you agree? So you have doublet, singlet, then I need to contract it. So it should be doublet. Then minus of 1. Okay. Let's take a look. Minus of 1. This can lead to 3/2 or can be half. Okay. I think, yeah, I'll explain it. So it will be minus 3/2. That you can see from here. Okay, let's give the arrow so that stood LEC. Yeah, so L is minus of 1, and this can be half or minus 3/2. Okay, so and here if I see, okay, maybe it will be explained by here. LL also should be contracted, so minus half and minus half. So it should be 1. There should be a particle, it should be some defined particles. Let me see, doublet, doublet, it should be color singlet, singlet, and it should be also 1. Okay. So that's how you assign the charges. So now you know, like if you have BSM particle, the simplest dimension 7 operator, if you are writing down, what should be its nature? There should be one scalar, say, give a nomenclature eta and give another nomenclature phi, and I need 2 type of scalar, which is giving 1, 1, 1 and 1, 2 minus 3/2. And that's the simplest G model. I'll tell it in a while. Before that, I will do this here. So here we are doing, say LL contraction, and I am doing EC and H contraction. Okay. Oh, sorry, I should have done the say LL EC H. And there could be somewhere a L will be there. Now, you know that what will be the particle here? LL should be scalar. And this is scalar, this is fermion, so I need a fermion also, BSM fermion. Okay. Now took the same strategy and you will end up with that. You will require a vector like fermion, like here, this side. Its charge should be 1, 2. Oh, sorry. I think I did it here. So this will be half. I'll explain it. 1, 2 minus 3 over 2. And this should be 1, 1, 1. There are two possibilities actually, but if you take the triplet contraction here, because you are contracting L and L, doublet, doublet, you can go through singlet or triplet. If you go through triplet, it will get some tree-level mass term because you are interested in the radiative model. So the one unique possibility will be just 1, 1, 1 and 1, 2, 3 over 2. And so you know the what ingredients you need. Once you can write down the this lepton number violating operator, you know that what sort of BSM particle you need. You see very nicer way. It's not like first we do just introduce a particle and then we see whether we are generating neutrino mass. You can do that, but that's not the way you should look at. Do systematically, take the minimal approach. What will be the simplest possibility? You will see that there will be finite possibility and you can come with the minimal radiative model. So this is the example which G proposed. So that's called G model. And let's take a look of the diagram. You have singlet. So I'm starting with, so whenever I'm taking some diagram, so say nu L, because I'm generating Majorana mass term, both should go towards. And now I am doing with a charge lepton, suppose say LL. Then I need a charge scalar, eta plus, which is 1, 1, 1. And then from this, as I showed you, LL, and then if it is a Dirac mass term, because you need 2 Higgs insertion somewhere, so it will be LR. This chirality suppression will be there. Always, I think in the beginning, I already told you, like whenever you write down a Dirac mass term, LL and LR, this direction flow should be go to same direction for the standard model other fermion masses, because that's not lepton number violating. You should keep track of the lepton number flow. So LL and LR. So you see, this is doublet, this is doublet, this is singlet. This is doublet, this is singlet. That means I require a particle which should be doublet. And that's it, 1 to half. It's another way of looking at it. Just diagrammatically also, then you can have maybe a cubic term, which you can write down in your theory. And whenever this Higgs, 2 Higgs is getting fed, you will generate the neutrino mass. Here you do not require any right-handed neutrino. You see that two way I came to the same conclusion. Taking the operator approach, I write down the selection rule, and I know what operator I can write it down from the standard model fields. Then I open it up, that particular operator. Immediately I can see that how only one way I can do some unique possibility. That way I know that these are the 2 particles I need to generate this radiative mass. And now also in another way, diagrammatically, I am seeing that also I need this, but just by looking at the contraction and so on. So this way you can generate the radiative mass models. You do the same exercise for the other cases. I'm just not writing down. So already I already showed you that 2 model you can just do like this way.
So can the data triplets?
Sorry?
Can the data be SU2 triplets? Why do you consider
This one? Yeah. So this one, can be triplet, but the problem is that that will generate tree-level mass also. So then I have no like why I should go for the radiative model. So to not to get in tree-level mass, I choose the 111. So that choose this unique possibility for the radiative models. But that's a good question. There are two ways it's possible, singlet or triplet. But if you take the triplet, then this is not good. So you see, these are we call type 1 radiative models. You can write down very systematically. It's not random. Whenever you see some radiative model, just don't be scared. Oh, there are so many, but how I'll know that this is the particle I need, and so on. So I will stop it here, or maybe just with the last comment, and then we can stop it here. So it will take maybe 2 more minutes, and then I will stop it. So basic idea is that I just give you an idea like how to generate radiative models by this operator-based approach. Okay, I'll just erase it. And want to show you the same thing you can do for higher dimensional operators also. So then another approach you can do, like which I just mentioned. Let me write it down. This I called graphical approach. I'll just show it to you, but again, the little pen probably maybe cannot see. It's really clear. So also you can write down. Suppose say this looks to me scary. Like okay, I don't know how to write down and so on. Those who are not doing model building also, you can take some defined approach also. So think about at the end of the day, we need to get a delta L equals to 2. So I need to generate LLHH operator. Think about how many possible way I can write it down. Okay, let me draw the diagram and I will tell you. L, and my Higgs can be here, Higgs can be here. These are all standard model field, okay? And then L, because I need Majorana mass term. So let's draw a diagram. My Higgs can be here, Higgs can be here. L, and then my Higgs can be here, Higgs can be here. Just where you are inserting the Higgs, that will determine, yeah, the last one is this. L. This unique fold topology, suppose if you want to generate in the tree level, like one loop level radiative models. As I said, its characteristic feature is that most of the model doesn't require any right-handed neutrino extension or any harmonic extension. Just scalar extension is like sufficient enough. So these are the four topology you can clearly draw. Okay, and that's the simplest possibility. Now you can think of, well, I can put here some LL. Suppose I want to go through the standard model leptons. Okay, suppose I want to go through standard model leptons, say let's write down ER. Then if you write down ER, you know this is doublet, this is singlet, I need a doublet. Do the same exercise, what you are doing. And then if it is ER, Higgs, then the flow will be same EL. And then if it is singlet, doublet, it's contract, and that's the G model. The same exercise you can do, even if you can do for the same case, just with a different approach. Like instead of ER, suppose I want to go through the quark. I can do that. So let's write down DR. Suppose I want to go through the down quark. Just instead of this colorless particle, now it will be colored. It will be some leptoquark. Okay. I'll tell tomorrow about these details, like maybe in a brief overview. So if you replace charge electron by quark, just these will be like defined leptoquarks. I think this will be doublet, so these are sometimes called R2 tilde. There are some 4 type of leptoquark you can write down in your theory, which have renormalizable interaction with neutrinos. These are called S1, S3, R2, R2 tilde. Is there anything I'm missing? No. So this is, I think, T1, 1/3, I guess, 3, 3, 1/3. There will be some plus and minus, I will fix it. 3, 2, 7, 6. I think 3, 2, 1, 6, something like that. But tomorrow I'll give you the proper things. Some there will be here and there 3 bar or -7, 6 and so on. So these are the 4 type of left quark you can write down in standard model gas theory, like which have denormalizable interactions. So if you are going through down, I think you need some R2 or R2 tilde because you need some doublet, and which is a colored particle. And here, if you need a singlet, it should be some S1 or something like that. So you will get a new model which will be colored radiative models. So same thing you can do it here also. The same exercise, just do it. Just like demand what you want, what standard model field you want. Accordingly assign charges, you will get a model. You will get a so my main idea is to show you this is not just random. If you are doing random, then you are not following any principle. There are some way of looking at it. You should take whenever you are constructing. If you want to do model building, my suggestion will be to take some minimal approach. Whenever I am introducing, I should introduce minimal particle in my theory without extending too much. I will suppose say one fermion cost more degrees of freedom than a scalar. Okay, so maybe the scalar, and I will maybe higher representation I will not use. If singlet solves that, let's do singlet, not the triplet. So because anyway, it will be part of it and so on. That's the way of looking at it, but I just give you an idea how to construct neutrino mass models in the tree level and radiatively. Tomorrow I'll give again an overview because we are running out of time, but I'll explain it tomorrow. Thank you very much.
We can also continue discussions outside, just to read the room. Let's do it. To have questions.
The game is